Okay, thank you everyone for joining us today. I would say, ladies and gentlemen, we are gathered here today to discuss physical exploitation of modern chips. Physical attacks on silicon are not necessarily a research curiosity anymore, right? The tools to run these types of attacks are an order of magnitude cheaper than they used to be 5 years ago, right? Open frameworks, hobbyist budgets, YouTube walkthroughs, right? The bench tier is real, right? Joe can attest to that. At the same time, the defensive literature has been addressing this topic for quite some time, right? And Domenic, you're here to talk to us about polymorphic circuits, right? Self-destructive registers and the like, right? It's been a decade-old engagement, would you say? And today we're going to walk through a specific scenario on one device, right? And address 3 tiers and one honest question at the end. Why is the defense not shipping, right? Quick show of hands here. Who has run a fault injection attack in the past 12 months? Okay. So we don't need a one-on-one on that, right? This audience is primed. Let me set the tone here. We're looking at the modern automotive microcontroller, tens of millions deployed out in the field, holds keys for immobilizer, V2X, ECU integrity, and the likes. And we want to explore 3 live attack paths at 3 different cost tiers, right? And then we want to find out why none of them sets an alarm off on the chip. Make sense? We're going to get started with Joe here. And Joe, you spent the last few years providing that single-person bench, right? You gave a lot to the open source community in terms of tooling. And you showed that with a few $100, right? And a lot of determination, right? Things could get done, right? Trezor, keep key, RoboForm, right? Walk us through one of them, sort of method level, if you will. What did the attack actually look like? What tooling, right? And what was the moment you knew it was going to work? I think that's, to me, probably the most interesting aspect. And let's connect back to this scenario, this hypothetical device that we're talking about, and explain to us how running the same playbook, right, would work today.
Yeah, sure. So probably like most people, I started with voltage fault injection on the targets that I was working on, which were the Trezor Model 1, STM32F2, that had some prior work with voltage fault injection. So I said, all right, I'm going to see if I can just replicate the public work that was out there. The tools were way more accessible. So with Colin O'Flynn, New AE, the Chip Whisperer, about $100, probably $1,000 worth of equipment. So I started there, had some sort of failures as far as like corrupting the chip. So following what was out there in sort of the public knowledge was like, okay, it works, but it's not reliable. So I moved into EMFI, which I hadn't done any work with before, the chip shouter. So a couple $1,000s for that. But the platform I built was actually like an Amazon CNC router kit. So not a piece of lab equipment. And I actually got it from John McMaster at hardwear.io must have been 2 or 3 years ago.
Yes, yeah.
Brought it home on the airplane, built it, and basically built a platform to do our whole methodology of kind of characterizing the device and seeing if EMFI was going to be better than voltage fault injection for this chip. So basically built a framework that we could characterize the chip, scan XY, and just using the capabilities of these tools that I didn't have to build myself. Like it was already there. So a normal person, can get into this world. They can get access to tools, they can get access to resources, tutorials, and make their own circuit boards for carriers and everything. And it really, the longest amount of time was creating that framework to do the scanning of the chip. And of course, doing the kind of campaigns to do the fault injection and determine crashing versus not.
So this brings up a good question right now. Would you say that pretty much anyone could do this?
Yeah, I mean, there's still the technical kind of learning curve for it. Technically, anybody could do it. I think the experience comes in knowing what the reaction is of the chip. Because a lot of times we're doing fault injection, we don't know, is it going to crash? Is it corrupting data? Is it doing something? And sometimes we don't even care as long as it's getting what we want out of it. But it's sort of knowing that thought process. And it's really this scientific process of logging, like when the chip resets, when it's normal, when it does what we want, and then narrowing it down. But it was a real learning curve for me as well, and took years to narrow it down. And in this case, EM worked better than voltage. But then we have a different attack that turned out now voltage works better than EM. So you never really know, but even if it's laser or whatever, like the tools are accessible. And from my world, being able to show this stuff and kind of demystify it means you don't need necessarily a top-end lab to do it. Maybe repeatability you might, but for just proving it or doing it on maybe a general purpose microcontroller versus the automotive, process would be the same, results maybe would be a little different.
So that's the bench version. Lionel, Joe just described that. So eShard runs the same family of attacks right now using probably what's considered higher end approaches, right, with your laser fault injection. And from a methodology standpoint, I'd like to find out from you, how would you approach a campaign like that?
Okay, so in terms of methodology, it will be quite similar to what Joe described. There is one main difference is, you said that sometimes we do fault injection, we don't know if it will crash, we don't know if it will fail, that's true. And sometimes it fails and we can exploit something. We don't understand what went wrong, but we don't care. We reached the point we wanted. And that is one main difference with what the industry would try to do. Because, for instance, when we work on these kind of chips, it's not for just fun. It's for a project. It's for a company. It's for the industry. So they will want to know why it crashed. How did you succeed? And how can I make it myself? Okay. So the approach is a bit different. And this is why we need to be able to explain what went wrong, when, where, etc. And in order to do that, if you use glitch techniques, the glitch power, voltage glitching is very global to the scale of the chip. And sometimes if you are only targeting the real asset that what has value in the device for the manufacturer, you are looking at the cryptographic keys or really specific IPs, and you want to know when it is triggered, what it is operating, and when you do fault injection on those, how it can be explained, basically, so that if a vulnerability is found, they have at least some ways to start addressing the issue. If you don't know what happened and you're fine with it, okay, you are successful. But for the manufacturer, it brings nothing but troubles. They have no clue on where to start addressing the issue.
I think what I'm gathering from both of you so far, that it's always nice to know what to expect. Is that a fair statement?
I think it's basically you know that you don't know what to expect.
Yeah. Well, that's what
but you have to be comfortable with that, right? Which is with engineering.
Be nice to know what to expect.
Yeah, you know that you don't know what you're going to get.
So Lionel, final lithography, chiplet packaging, package on package, etc. From a lab side, which has had the biggest practical effect on how you approach a fault injection or side channel engagement? Right. Walk us through one.
Yeah. So I would say the evolution of the packaging, lithography, those are not what we could call countermeasures, side channel countermeasure, fault injection countermeasure, but they are by nature. So they are not made for security. It's for optimization, whatever you want. But actually, for instance, on the lithography side of things, when you work with a few 90 nanometers, so that quite old technology, we can still, with a laser system, which can focus the laser beam down to 1 micrometer, target a bunch of transistors or some specific logical circuitry. When you go down to 14, 7, 3 nanometers, you are targeting with a single 1 micrometer laser spot already hundreds of thousands of things on the silicon, and you don't know what is going to happen. So it's way harder to reach the point where you can create a fault with high repeatability in order to reach the point where you can exploit something. So the lithography itself, it's not a countermeasure, but it makes the problem harder. Another thing, frequency of the devices. When let's say the attacker, when you do faults on smaller microcontrollers that will operate at few tens of megahertz, then we are talking hundreds of megahertz. Then we started to talk about gigahertz. The nanoscale laser systems, which are I would say, most common one, are still good enough to inject faults and get something out of the chip.
So you've hit on some of these notes already as you were explaining this, but I'm wondering if you can go a bit deeper and tell us how tooling had to evolve.
Yeah, so if I still focus on lasers, you see that because of package on package, you do not have access to the chip directly. You need to do lots of things, opening the device, sometimes breaking parts of the circuitry, sometimes removing completely part of the circuitry to create custom PCBs. So I guess you know pretty well what this is about. Creating custom PCBs, and then you can start working. But it's not over. You need to characterize the signals. You need to handle, is this BGA, it is the kinds of wire bonding that are in place. So it's way more complex to do. Of course, the preparation, if you do laser, to have the silicon visible. So all the decapping, do you use mechanical, do you use chemicals? That's very dangerous. You can just die with the wrong usage of the chemicals. So it's really complicated. And if upon that you also add chiplets, high frequency, and all the things, that becomes really a nightmare, and you need more tooling just for preparation.
Understood. Lasers, chemicals, it seems like dying is a real risk here. So Domenic, you have argued the conversation needs to include 3D IC and chiplets explicitly. So from an attacker's perspective, what new surfaces do these architectures introduce that most practitioners haven't had to deal with yet? And from a defender's perspective, do they help, hurt, or neither?
That's a great question, and I like how you phrased the very end of it. So yeah, I think it's a bit of both. So first of all, in terms of hurting, you're definitely expanding the attack surface, the side channel surface and fault injection surface, because now you have chiplets within the same package, which could actually be attacking each other. And when you're within the package, the signal noise ratio is much lower, right? Whether you're doing a fault or you're eavesdropping. Now, in terms of defenses, it could also help, just like you said, with a package on package. So I know Intel has this power via technology. That would also be pretty interesting, both from an attacker's perspective and defenders. So for example, if the power is actually in the silicon now, does it make voltage fault injection easier? It's actually accessible through the silicon? Or do you think of that as more of a barrier that if, say, you're doing some chip editing, it becomes more difficult to reach certain things? So it's always a bit of both.
Got it. And Joe, as you've been listening to these two takes here, is this something that you're already seeing in the wild? Is this something that is doable right now with accessible tools, or this is still a bit ahead of the bench tier sort of frontier?
I mean, the thought that's been going through my head is like, wow, that stuff sounds awesome. But in the engineering world, how much of it is actually adopted, right? You have like super high-end stuff where you do have capable devices integrated into things. But so many things are still using lower-end devices. I think it's really the processing side of things. And we've even seen like decapping where, Hash gave a talk about it here at hardwear.io last year, I think, about decapping chips in his garage. And like that has trickled down to something where nobody would do that a couple years ago or 5 years ago. But that's still deprocessing single chips, not, package on package. So I think it's getting there for certain things. I think a lot of it in my head is like, okay, maybe is there a way to get by or do some faults or attack the device without having to do the high-tech deprocessing. So maybe there is a mistake in some implementation of something that we can take advantage of. And as far as the chiplet stuff, yeah, I mean, if there's multiple devices in there, and like then you start thinking about the hardware implant side of things like that's a whole other thing. But that's also fascinating.
And they're sharing a power network. I mean,
yeah, you're right. Just do your side channel and then use that as the trigger. Yeah.
So you mentioned hash. I think for me, 3M has never been the same since I got to know his channel there. Yeah. So and this is for all of you, but I'd like Domenic to give us the first take with software-induced sort of physical attack and clock and voltage manipulation from a compromised peripheral, Rowhammer class effects, remote glitching, right? Domenic, you raised this on a call we've had, and I'm wondering how close we are to a world where physical exploitation does not require physical access, right? And what does that do to the assumptions baked into the device's security model, right? How do we need to reframe our thinking around that?
Yeah. So again, that's a great question. So the move to, I mean, we've seen this already with microarchitectures themselves, performance optimizations over security. And again, with 3D integration as an example, we're doing the same thing again. We're putting performance over security without really thinking about it. So I'm sure most of you are probably familiar with the CHIPS Act, and there's lots of work on devices and 3D integration, but security is still like the second-class citizen, and it's not being considered with those two, which is where it really needs to be considered. So before we roll those out, we really need to be thinking about those in terms of security.
Lionel, your take on it.
Yeah, I think this complexifies a lot the problematic. So chiplets in particular, indeed, I think they're complexifying the traditional physical attacks where you need physical access, you need like physical means to prepare and everything, because you will have like new ways to explore or to monitor internally some data that will let you or still give you access to some other side channels. But in the perspective of, for instance, real physical laser fault injection or even EM, I think this is really not a road blocking, but not far for, I think the classical methods.
Joe, does the remote tier change what a single person attacker can plausibly do?
I don't think so.
Oh.
Yeah, I think it possibly even opens things up, because now you don't have necessarily you don't need a hardware lab. It's a different sort of attack. So yeah, I think it's probably.
Would you say that trivializes the hardware aspect, or would people still need to be very much aware of what they're doing?
I mean, I just think about like at a high level, like Shodan and IoT, right? You have all these devices connected, and people don't necessarily even care what the hardware is. They're searching Shodan, they're looking for things that are connected, and they're attacking those. So I think on one hand, there will be interest in like, oh, what are the capabilities of this chip I'm hacking? On the other hand, if you can do anything remote or any software controlled attack, it's just going to open it up to a lot of people who don't necessarily care about what the actual underlying architecture is. It's like, we want to hack that.
Yeah. So again, what was interesting about our conversation, especially Joe's talk this morning, was that it really opens up a new axis, these hardware implants. Because what you showed is that they were actually just sending information off. So they were actually creating a physical attack that worked remotely now through the implants. And they were using it just to go in that direction. You could easily go through the other direction as well, right?
Yep.
So you could actually have these implants for hire, and then people who just use them, right?
Yeah, for sure. And the system level hardware stuff, which is what I typically deal with, like those are easier to find. But if it's a chip level implant, nobody's really looking. They, in some situations they are in academic world and kind of spot checking, but it doesn't scale if you're checking for implants on everything, unless it's like Bunny's iris kind of infrared in situ examination of like chip scale packages. But in general, it's way easier to hide something in silicon than not. Yeah, so it's definitely interesting where people can even make their own chips now. And through, I think it's wafer.space, and there's, kind of circuit, like Osh Park for circuit boards. Now people can bundle their designs into silicon. So I think we're going to see more malicious implants, and then those get packaged into something. And then if it's just passively exfiltrating, or if it's intentionally now having some remote access or doing something else, it's board level stuff at a microscopic level.
So we're here at hardwear.io, and I always seem to find these gray areas, right? And ask myself the question, where does this stop being physical and start being software? And is that distinction still a useful distinction?
I would say yes. Simply the way we call it, like physical attacks. So it relies on physical quantities, whether we talk about timing, energy, or space. So this will still matter. It's just in order to measure those, for such, we use probes like EM or ELS. For injecting, we use EM coupling, we use laser beams or 2-photon absorption, so different kind of techniques. But still, we use physical means to modify the physical behavior of a device. What's new here is your probe, your sensor is embedded on the target. So as soon as you have access to it, maybe you don't need to consider an external lab facility to get or to measure things because it's already inside. You just open a communication channel, you get the information, and you have some insider probe.
Your guys' take.
Yeah, I totally agree. But again, this line between software and hardware that gets blurred is really with the microarchitectural attacks, right? So some of you may be familiar with Chris Fletcher's work on DVFS and turning that into timing side channel, which is pretty amazing stuff. Again, it's kind of bridging the two. So yeah, I'd say that's the line: software versus hardware through the microarchitectural attacks.
So getting back on track, I think we wouldn't be here in 2026 if AI wouldn't enter the chat, so to speak. And AI shows up in these types of conversation in two ways. One is an accelerant for attacks, and as embedded inference becomes now a target, right? Yet another thing to go after, right? Which is the more urgent problem right now, Lionel, with when embedded AI inference runs on a chip that does its power trace or EM signature, or what does its power trace or EM signature look like, and what could we potentially extract out of it, right? So when we use inference on hardware, right? And then the next question, I guess, or the next angle that I'd like to take into account here is, has AI at all helped any of you in doing better, faster, more?
Okay, so interesting question and trendy question, I would say.
Yeah.
On the AI, so some companies are already developing IPs using neural network to provide some features for video processing, these kind of things, etc. So I talked before about assets. In the case of for the industry, you have an asset that is defined, cryptographic keys, etc. So now your neural network that you're loading on the chip is an asset. Okay, so from our perspective, this asset needs to be protected. So with the classical methodology, how your asset is behaving, what is the input, what is the output, what can you measure, what can you count, etc. So in the case of inference model, you will have a weight that will be set, and this is the kind of things that you will measure. But the problem is when you have like an execution of, let's say, ECC, RSA, or whatever, you know more or less when it starts, when it ends, and what is supposed to happen. When you have a neural network, how many layers do you have? What is the ranges of the different values? So in order to build your model and use then statistical tools like correlation-based, differential, etc., the models are more complicated to manage. And also the duration of the acquisition might be also bigger. It's way more messy. So the SNR basically is very, very bad when you acquire traces on when recording this kind of activity. So the attacks are also more complicated. So the usual way would be to have some ways to characterize something, a model that you have built, try to characterize the chip, and then try to attack something that you have loaded, another neural network, but still it's way harder than the classical sequential algorithms that are used for crypto, for instance.
And how has AI sort of aided to your work?
And so, for your second question, I would say, especially now you have lots of libraries that exist, lots of contents that exist, and maybe you have ideas, but you don't know how to implement that. I think AI is powerful in that sense. You use reinforcement learning for some models on databases of attacks, on libraries, open source libraries, and then you have your ID to create your attack path. You just don't know how to do it. Now you can use a chat bot assistant, train on those resources, and ask it, okay, I have this specific implementation. I would like to attack this specific moment during the encryption, if we are talking encryption again, and then it can help you build the specific custom algorithm, custom attack path that you will need. So that will save you a lot of time, and you can, with more time, explore even more attack paths. So I think in that sense, AI is really helpful.
Okay, thank you. Joe?
This is going to be a naive view because I haven't like dug into LLMs or all that stuff. And yes, I've used them, which I can answer that. But my sort of view is like, if there's something on the chip, it's another resource, it's another potential avenue. It's probably going to take more characterization. But my sort of cynical view of being around for so long is that security is not one of those things that's being focused on. It's getting AI working. It's getting it on the chips and getting there first before other people. So side channels and those sort of secure coding practices around that are probably not going to be in there. So there maybe is going to be more leakage of things that we can pick up. So it's going to make our characterization easier. I just don't, I can't see that security is going to be an important part of at least the couple generations of chips until people start hacking them. And even then, we see that security is not sort of rolling into everything anyway. So I think it's just another interesting potential attack vector. As far as using AI, I originally sort of started using it. I had installed a Ghidra module that could basically take the decompiled function and it throws it into ChatGPT and comes back with a text description. And that was my first. I'd sort of been avoiding AI until that. I was like screwing around with it. I'm like, this is actually a pretty good time saver. I've been using it a lot as sort of a way to kind of, it's like when you used to post a question on Twitter and it's like lazy Twitter, like how does this work? And all your friends answer. It's sort of like that where I'll throw binaries into it and just get a general sense of where I need to look. I haven't done anything with AI and fault injection, but I know even the past couple of weeks, there's been a couple talks on it. And of course, the one this morning with Jasper is sort of the other way of fault injection against AI. But there have been talks about using AI in a way to help analyze your glitch campaigns and your data. And I've used it to help me plot the data, mostly because I don't want to spend the time trying to figure out how to do graphing when I'd rather do hacking. But yeah, I mean, it's definitely one of those tools you need to still question it. But if you know what you need to get out of it, I mean, I'm not going to lie. It's like saved me hours and hours and hours of work on the things that are less important. And that saves time, which means the attacks are going to work better. And then I can focus on the stuff that I want to focus on that the AI maybe can't do, the physical stuff and prepping it and doing that. So yeah, it's been an interesting tool and like a good assistant. But it's always a trust but verify kind of
Understood.
thing.
Domenic, your take.
Yeah, so in terms of using AI, I think I use it more or less like Joe does, just bouncing ideas off of it, seeing its feedback, that kind of thing. But what scares me most is really that like I saw in the talks today, it can definitely help accelerate your attacks, especially if you have, a platform where you're running the attacks and you're feeding it data and summarizing the data for it. But what scares me is that on the defense side, it's very asymmetric. To train AI, you need a lot of data, and our hardware typically is fairly fixed. We can change firmware, we can change software, but we don't have a whole lot of reconfigurability in there. So, if you're trying to assess your hardware, you can't run simulations to feed it every single possible configuration and have it figure out the best one. And we don't have hardware that's malleable enough to do that live and find the best configuration. So that's the thing that really scares me, how asymmetric this really is.
Do you still think, to Lionel's point here, that inference on device and AI on devices, if we're to use the general term, is still, something that's new, or is it, much to Joe's take, the same old in terms of the goal is the same. It's an asset. You need to have it extracted, right? Lionel shared some variations in terms of how you look at that, right? What's your take on it?
I would say it's still more or less the same as well.
The same.
I mean, the foundation is the same. Maybe the goals are slightly tweaked and slightly more ambitious.
As my wife always reminds me, is that there are no new jokes, just new people. Yeah. So Domenic, we've walked now through all of these 3 tiers, and none of them set an alarm on the chip itself, right? You have published on polymorphic latches, self-destructive registers, sense and react, voltage tamper detection, etc. Defensive primitives that would have caught many attacks, right? They're not in the devices that we're looking at today, right? Even in this hypothetical scenario, right? They're not in any device. I guess anyone in this room has on their workbench, right? And I'm wondering, how far is your work from production silicone, and what would it actually take to ship it at scale?
So the polymorphic registers we're making a lot of progress on. We haven't, I think that the limiting factor right now is we haven't demonstrated in silicon. So that would be the first step. But my colleague at the University of Arkansas, who developed like the based technology that we're kind of exploiting for this, he has tested it in silicon, and it works. He's just never looked at this polymorphic behavior. And yeah, let me just give everybody a quick idea of what I'm talking about with that. So this was invented at Jet Propulsion Lab in around 2002 or so. And the idea was that it was a circuit that could do multiple functions and changed its function in response to the environment. And the limiting factor is it was only being used basically at the gate level, and they were very, very hard to design. They were using evolutionary algorithms and things like this to make it work like they wanted to work, because at temperature X, it's supposed to do this, at temperature Y, it's supposed to do that, or at this voltage, it's supposed to do something. Very hard to do. My colleague at the University of Arkansas developed this technique, which you could now do manually, very easily, and predictably determine how to control the polymorphism with voltage. And so I took that and I used it in a register where the first function is just the normal functions. So with all of these latching elements, you have a transparent mode, you have a hold mode, which is saving the data, and that's it. But there's also an unused mode, which would be bad normally, and that's the metastable mode, where it's not really holding its data. It's really hitting this area where the data is destroyed. And that's the second function that we're incorporating for the polymorphic behavior. So based on voltage or based on temperature, we have 2 different versions of this. If the attacker is lowering the voltage by a certain amount that we know, we control the threshold, it'll actually destroy the contents of the data. And it does it within the register alone. So this is something that happens locally. It won't take hundreds of cycles to self-destruct the data. It just does it in an instant. So again, the limiting factor is we haven't demonstrated in silicon yet. I have a proposal which hopefully gets funded, and we'll be able to do that. And the idea is also to be a bit more ambitious, to go beyond just registers, to go to whole IPs, where we're using polymorphic behavior as well.
Is the industry asking for these types of countermeasures?
I would say no. And the reason is they're not like all the folks here. They're not really aware of what's going on. And to Joe's point earlier, security is always like lagging behind everything, right? So we used to talk about this all the time in like the host community. Things are not going to change until there's a hardware 9/11. And so they're just not looking for these things.
From your perspective, who would be the best sort of entity to ask for these countermeasures? The buyer, the manufacturer, the regulator, the insurer in some cases. What's your take on that?
The insurer is a good one, especially again if these crypto wallets keep getting hacked, right? Or the security tokens are getting hacked or eavesdropped. Yeah, I mean, insurance has to foot the bill on some of those, either for the company producing them or the people using them. So I do think that they have a lot of skin in the game. And the same goes for critical systems as well. I think the insurers and the people who are making investments in those companies, they should have a lot to say about it.
Got it.
And then like the other thing that would speed this along too is if the manufacturers had these IPs that they could just they could just drop into the chip and then use them.
If you could put just one of these primitive into every secure microcontroller shipping in 2027, which one would it be?
I definitely think the polymorphic one is really, really impressive because, again, you could have it be controlled by the supply voltage, but you could also have a sensor sensing anything, which is just controlling the supply line of that register and connected to it in some way. And I also left out another way that we use it as well. So for privilege escalation, we're trying to, force the state registers into a certain configuration. Well, this polymorphic register could also force you out of that or to a reset based on voltage or clock or whatever glitch it's actually sensing for. So again, it's all built in, doesn't require any additional circuitry. It's all in one.
So we've heard from you, Domenic, and quite the avant-garde position there. And I want to sort of pose the hardest question, I think, at this point to Lionel and Joe. From your sides of the table, what is the actual reason that chips don't have this, right? So from an attacker's perspective, is it cost? Is it that silicon vendors just don't believe in threats, right? Is it that buyers don't ask, or pick one, what comes to mind, I guess?
I don't work at a semiconductor manufacturer, so I don't know what they're thinking. But there are plenty of vendors that know they're vulnerable, and they have devices in the billions in the field and refuse to update silicon, refuse to patch them. One company I'm not going to name, I had actually emailed them when I was doing some of my fault injection work, and I was wondering if they had patched the chip. So as I was characterizing my chip, I wanted to make sure, is it still vulnerable? I emailed them as an engineer and said, hey, I'm interested in designing with this chip. Are you aware of this public research that's out there? They said, oh yeah, we're aware of that. We haven't fixed the problem. We recommend using this more expensive secure microcontroller. So they're trying to upsell me instead of fixing what they know is vulnerable, what they've known for a long time. And this is not limited to one vendor. So it's probably a financial thing. It's definitely a pressure thing also, because I had looked at multiple chips from the same company. Some of the chips did not have countermeasures for fault injection. Some of them did. And that particular device apparently is used by the US government in something where maybe the family I was looking at wasn't. So it's sort of this selective increase in security, which is a little bit frustrating. It's great for me as a hacker and for job security to teach people hacking, but it's super frustrating to be, basically 40 years in an industry where we're still using antiquated protocols and technologies, and that there are solutions and interesting solutions that I think will never end up being in every type of microcontroller, only high-end stuff. But until vendors are pressured to actually incorporate security into all of their chips by everybody, not just a hacker telling them their baby's ugly, they need to sort of respond to that. And like what Domenic said is, there are people that are not like us that are running the companies, are running their management, and they're not necessarily thinking about security. But it's it's super frustrating to see it not making it as a good a change as we could. We see it on high-end chips. Things are getting potentially better, but in general, it's just, there's a long way to go.
Okay. Lionel, does that match what you see from the vendor side?
Yeah, I completely agree with what both of you said. And people will try to upsell you the best class thing that will go for certification. So the marketing is great. It's the best thing ever, AI everywhere, etc. So that's true. People will try to upsell. And in order to force them, usually it's because you will have higher stake assets again. So I'm talking always about assets. But if you work, for an IoT camera, if you have an IoT camera, some small device, like low-end device, maybe it's not even necessary. You have like full software countermeasure that could help. But if it's governmental facilities, weapons on the fields, the game is completely different. And this is why governmental agencies usually have, I would say they are managing independent evaluation labs that will enforce a minimum security, and then you have grades of security. And manufacturer will need to respond to this request and provide higher grades and higher end countermeasures. And these kind of countermeasures, polymorphism, especially at the register level, I think, as you said, the way to make it more available, I think, would be to manufacturers to add them into their IP buckets and propose that to people so that they can see and use by themselves, and then see, I would say, for the risk management, if it's worth it to go for that class of device or downgrade or upgrade according to what it will be used for. So money is a big question here.
I want to kind of ask you one last question, right? And we've talked about this a bit. If you were to impart a message to this audience who sits on both sides of the fence, right? The manufacturers, the attackers, and so on. What would it be, that one thing that you'd want this room to do differently starting Monday? And we'll start with you, Domenic.
Yeah, I'll take inspiration from the keynote this morning, the future-proofing idea, and I'll sort of expand on that a little bit. So in the last year or so, I've been looking into cyber-informed engineering, or CIE. I don't know if anybody's ever heard of it. Something being developed out of the Department of Energy. And it is critical system focused, but even the hardware that we're working on are systems. Even the chips are system on chip, right? They're all systems at the end of the day. But it's a 12 principle framework that you follow. So if you're not an expert in designing and building things or making things safe and resilient, you could apply this, and it really helps you do things systematically. So I'd encourage you all to take a look at the cyber-informed engineering framework. They're putting out lots of materials, implementation guideline, going through the principles, databases, lots of things, lots of cool resources, which I think could really help this community future-proof things.
I would look at the devices you're using. I would question what the vendor is telling you about those devices, and I would push back and ask them to prove how the security works, regardless of level of chip. Any security that's in there, a lot of times they might have a false sense of security, or they think they're doing something in a way that's helpful. But putting pressure on them to explain what they're doing, and if they're not doing something, then put pressure on them to try to integrate security in, because if you threaten to go to a different vendor, that's the money. Your wallet talks, and I think that's really the only way to get people to really start worrying about security.
Yeah, I would say if you are in the academia, start. Play with the tools that exist. You have lots of open source frameworks for the software side of things, very cheap hardware. So please start. Even if you are not expert, just start the basics, and you will see you will be hooked, and it will never be over. If you are more in the industry and you are trying to get budget to buy some interesting toys for your team, same. Try tomorrow, maybe not tomorrow, but next week. And it will be rejected, of course, but try again and again. And at some point, you will have someone that will follow you, and you will have your toys, and you will be able to try with higher means than the academia, because maybe your company will start to consider security, and you will have then to prove them that their investment worth it. So try.
Thank you. And I think what I want to impart to the audience here is that I think this conversation hopefully brought to fore the fact that the attack stack right now is democratized, right? It's easily accessible. These folks are the proof of it, right? The research, there is no research gap, right? We seemingly have solutions, right? I think the only item that we're missing is a deployment gap. And if I can address all of you, I would say that is your work now, right? I'd like to thank all of you, and please join me in thanking the panelists.